Hello everyone, and welcome back to another video from the Lighting Controls Academy. I'm the Education Manager for the Lighting Controls Academy, Webster Marsh, and today we're going to be talking about dimming control. This is the first part of a multi-part series, the Introduction to Dimming Control, and it's broken up into 4 parts. The first part we're going to go over the fundamentals and core concepts of dimming, then the technologies and control methods you might experience with dimming, the dimming applications and control strategies of dimming will be following that, and then finally design and documentation of dimming systems. So let's talk about the fundamentals and core concepts. First, we want to ask ourselves why dimming matters. Well, the first obvious thing is that we want an output that is instead of on-off operation. We want that because it improves the comfort and visual flexibility of a space, and so we really do see an improvement over the quality of the illumination in the space when we are not just switching it on and off but also dimming it. But we also see a lot of other benefits, such as daylight integration, where we can then adjust how much light, artificial light, is being provided in the space to compensate for how much daylight is already being contributed to it, and also just general energy savings on top of not just daylight integration, but other kinds of energy savings. And we also have this ability to enable scene control and create specialized lighting environments to support any kind of need just by having this ability to adjust the intensity of the fixtures. Finally, we are also seeing that energy code really does require dimming. And so more modern energy codes are starting to become more and more strict about what that means and how we're controlling for it. And so by having dimming, we are also meeting those code requirements. So let's talk about dimming with modern LED systems. So with most modern dimming systems, we are primarily talking about LED-based fixtures nowadays. We do see every now and then still some other legacy type systems or some newer systems that really aren't LED based at all. But for the most part, with commercial and industrial and residential, we are most likely going to be dealing with LED. And with an LED system, we're oftentimes seeing a driver which is delivering power to those diodes, the LEDs, light emitting diodes. And so that driver really does control the intensity of the LEDs. The dimming quality really depends on the driver and the controller's compatibility together. So the controller sends information to the driver, whether it's via phase dimmed or 0 to 10 volt or DMX512 or Dolly. All of those are coming from the controller, being sent to the driver, and the driver is deciding what happens as a result of that information to the diodes. So having smooth operation really requires a well-coordinated design system for those drivers and thinking through that compatibility with the driver and the controller. And so dimming often works alongside other control strategies. It's not a standalone feature that is going to work by itself. It oftentimes is going to be best coordinated with time schedule or occupancy sensing or dynamic scene control. All of this is just one piece of a much more complex lighting control system design. So when we're talking about dimming, there's actually various ways to dim, and so you might hear these terms, although continuous dimming, which is kind of becoming the standard requirement nowadays, is sort of where we're heading, but we're not 100% there yet. But let's just talk briefly about these different types of terms. So switching, that's when we're talking just full on, full off. That's it. There's no in-between stages. There's nothing else. That's all switching is. Step dimming, on the other hand, we're talking about multiple preset light levels, which might be stepped to create different intensity values. So you might have an off 50% full, and you don't have anything in between those steps, but it is a noticeable transition between those levels. Whereas continuous dimming, this is when we're seeing smooth transitions across a dimming range. So instead of seeing that, off 50% full, we might see a gradual shift from off to full or off to 50%, and it's not as noticeable a transition. And continuous dimming really is preferred for the comfort and even for daylight response because of the fact that it's not as abrupt, not distracting for the people in the space. And so having dimming paired with other features such as daylight control or occupancy control can actually improve the occupant's comfort in the space. Dimming range, so that was a term that I just threw out in the previous slide. This is how we're defining how low a luminaire can dim. So for example, 100% to 10%, 100% to 1%, 100% to 0.1%. These are all dimming ranges that are available in fixtures. And what this means is that the lower number is what determines how low the fixture can dim to. So in a 100% to 10% fixture, it can only dim to 10%. It can't dim any lower than that, which is common in 0 to 10 volt dimming, which we'll talk more about later on in this presentation. But the 10% requires a relay to then switch the fixture off. And so you're going to see a noticeable shift at that low end. That's why 0.1% exists, because it has a much lower amount of light that is going to be switched off at the end. So different applications require different ranges. Range should really align with the occupant needs rather than just, flat across the board doing 10% or 0.1%. 0.1% typically comes with a higher price tag. And so as a result, you really want to make sure that you're applying the right percentage range to the right space needs and application. On top of the dimming range, we also have the trimming and the performance of the fixture. So these are terms that are common. High-end trim, which is where we're limiting the maximum light output. So instead of allowing the fixture to be able to go to 100%, we're now limiting it to 90 or 80%. So if you hit the full on button, it will only go to 80% instead of its full range. And this really supports what's referred to as task tuning, or it might even just enhance energy savings, because oftentimes we don't really notice the difference between 80 and 100%. And so skimming off that top 20% will save some energy while not really impacting the results. Additionally, if there are fixtures that have a huge amount of output, we can tune those fixtures to a level that makes more sense at its fullest level than having to, potentially create an uncomfortable condition for the people in the space. Low-end trim is the opposite of high-end trim, so it limits the minimum dimming level. So instead of it being a hard limit like in a driver where you just can't dim below, we're actually creating a programmed minimum to prevent that fixture from going below that level. And that might be to prevent some unsavory dimming capabilities at that low end of the dimming curve, because we don't have a high quality compatibility between the driver and the controller or something. So we trim out that bottom area where we see those undesirable results. So talking a little bit about dimming range versus trim, really range is the driver's capability. It's typically fixed. We can't adjust it without going outside of the manufacturer's provision of the driver. Whereas trim, we're programming this behavior. We're now imposing an artificial limit on the fixture or the zone or group to make sure that it doesn't go outside of parameters that we've dictated. Fade rate, on the other hand, we're talking about the transition between light levels. So it's not just, okay, where are we dimming to? Are we going from 100% to 50%? But over how long is that fade going to happen? And so slow fades we might see in hospitality settings where we want, low impact noticeability when we're going from the daytime lighting to the nighttime lighting. healthcare, where we don't want to shock patients with just sudden on, sudden off lighting. Presentation spaces, where we want to gently bring people into the mood of being receptive to a presentation. Whereas fast fades are typically for energy management. We just want, that instant response so that we can reduce how much energy is being used by the fixtures. If we just want some general occupancy control, so, walk into the space, the lights turn on, leave the space, time out, the lights shut off, that might be where faster fades come into play. But we really want those fades to match the user expectations. So if somebody walks into a space and the lights turn on too quickly, and that certainly can happen, that might actually be a less desirable result than if we had a slower transition from off to on or off to 50%. And so just making sure that the user's expectations are aligned with how long or slow our fades are going to be. There's also undesirable things that happen with dimming. So pop on and drop out. Pop on is where the light jumps to a higher output before dimming happens. So, it might be as you're adjusting the intensity, it just suddenly spikes up to a different intensity. That's pop on. And it really does create these uncomfortable transitions between one state and another. And this is most commonly found in phase dimming, but it still does exist in other dimming conditions, but it's very, very rare outside of phase dimming. Dropout, on the other hand, is where lights turn off before reaching their target low level. And this really reduces that dimmable range. We see this also in phase dimming, but we see it in other kinds of controls where the fixture either has a floor in its driver and it has the capability of shutting power completely off to the diodes without a relay, but this kind of, again, it limits what you're able to dim the fixture down to. And so dropout and pop on are really undesirable results of incompatible driver controller relations. How we prevent it is we want to make sure that we have the right driver selected and we verified that it's compatible with whatever controller we're using. So manufacturers, especially in phase control products, we see that they have actual compatibility test reports. And so you can actually go to their website and see which dimmers, which lamps, which fixtures are compatible with which controllers. So talking a little bit about what I mentioned before with human perception of brightness, the way we perceive brightness is not in a linear format. You can't really, as output increases, our perception of brightness is decreased. It's logarithmic, which means over time we'll actually notice less and less difference. And so even though you're adjusting the instruments, the fixtures, the zone in a linear format, 100%, 90%, 80%, 70%, we actually don't really view lighting in that same way. And so when we're selecting dimming curves, which we'll talk about in a moment, we want to make sure that we're keeping in mind that people don't function in that linear format. And so that's why we have other kinds of dimming curves available. So dimming curves, which is what I just mentioned, we have linear, which is what most people view as a standard dimming curve. Its output changes proportionally. So 10% is 10% of the fixture's output. 90% is 90% of the fixture's output. So with square law, we're actually trying to align with the perception of people so that we make it a little bit more correct to what people expect from their dimmer. So we make it so that the very beginning of the dimming curve is quicker. And so between 0 and 10% on the dimmer, we might actually have between 0 and 20% on the fixture's output. And this much more aligns with our perception of intensity and brightness. It's not as common with drivers because we actually have a different curve, which is logarithmic, which instead of aligning with perception, actually draws out the low end of the dimming curve by allowing us to have more granular control over that low end. So between 0 and 10%, we might actually only be controlling 0 and 5% of the fixture's output, which gives us much more fine-tuned control over that low end, because that low end actually is much more noticeable than the high end of the dimming curve. And so we'll start going, very slowly, and then it'll start picking up as the fixture gets brighter. And then between 90 and 100% of the dimmer's assignment, you'll see on the fixture's actually providing between 80 and 100% of its output. But you don't notice it that much because of the fact that your perception of intensity has altered. I'm not going to get too much further into the weeds on that, but I highly recommend you check out, there's some great literature by the IES, the Illuminating Engineering Society, on perception of brightness. And then finally, there's custom curves. So we might have application-specific performance depending on what we're trying to control for. It might be color-specific, where we picked one color and we're trying to fade to a different color, and in between those 2 points on the color graph is a really ugly color, so we create a custom curve for those colors. But custom curves really do provide much more specificity to dimming capabilities and may not be appropriate for every application. And so typically we see either linear or logarithmic being applied to standard static white interior spaces. So getting into the technologies and control methods of dimming, first I want to address legacy dimming technologies that are out there. For a long time, we have had a lot of other sources out there that we've been controlling via dimming, and we're no longer really seeing that being used anymore. LEDs have really won the competition, and so they are in the choice of lighting control systems nowadays. But just to kind of address the elephant in the room, the very first type is incandescent, and that's where we found phase control dimming to be the most effective, and why we still have phase control dimming, because LEDs have found a way to be compatible with phase control dimming. Fluorescent, we've seen with dimmable ballasts, we've been able to create dimming capabilities within fluorescence, and this is where 0 to 10 volt came out of, with a need to, instead of using phase control dimming, we needed a separate control circuit to be able to tell the dimmable ballast what intensity value to go to. High intensity discharge, or HID, we really saw a lot of limited dimming capabilities with, and while we could certainly dim them to a degree, we had a lot of unsavory results with dimming high intensity lamps and fixtures, and so it was quite challenging to provide a quality dimming experience with these fixtures. And then there are other specialty sources that we've seen where we needed dedicated transformers or power supplies to be able to communicate the intensity value to the fixture or to the lamp. And so as a result, we really have stepped up in ease of use with dimming with LEDs because of the way that they behave and the way that they are powered. In comparison to at least HID and fluorescent, we've seen a lot of benefits and in ease of use. Incandescent, it's debatable. A lot of people say, incandescent dimming is so much better than LED for a number of reasons, but we've actually seen the innovation of LEDs with quality dimming and the correct communication protocols in place that we have actually high quality dimming that is competitive with incandescent dimming. Going into sort of LEDs and their common driver issues, because it really is sort of, again, that compatibility between driver and controller, we see a lot of weird behaviors like flicker, shimmer, where it's not stable in its intensity. audible noise, which is less common with LEDs, but it still does happen, especially when we're dealing with larger drivers. Uneven dimming, so you might have, one group dimming at one intensity value and another group, or you might see like a gradient. We see these unsavories like pop on or drop out, or we might have, again, that limited dimming range to really prevent it from being able to go too far down. But let's talk a little bit about how we get there. So what is going on between the driver and the diodes? The most simple example of what is happening between the driver and the diodes is pulse width modulation, or PWM, which is where the driver is rapidly switching the LEDs on and off. It's just so rapid that you can't see that it's turning on and off, but your perception of the intensity coming out of the diodes is lower. And how we adjust that brightness is based on how long those diodes stay on in that imperceptibly small amount of time. So the longer it's on, the brighter it seems. The less it's on, the dimmer it seems. And as a result with this, we actually have a really wide dimming range and good precision with the intensity of these diodes. But if it's not well implemented, this is where we do start to see flickering, or where imperceptible flicker can cause migraines or headaches, or even caught on camera and creating weird striations and stuff. So there is some limitation to what PWM can offer, which is where we get into other kinds, like constant current reduction, or CCR, which is where we're reducing the current, the amperage supplied to the LEDs, and it creates a nice smooth dimming performance regardless of, so long as it has that constant value of current running to the diodes. We're going to have that nice stable value. So if you take a camera and you start recording, you're never going to capture weird flickering. And so as a result, there's a lower risk of flickering happening with the CCR type of application. Constant voltage reduction, on the other hand, is where we're doing the same but using voltage instead of current to adjust how bright the diodes are. It's very common with tape lights and accent lights where you might have a varying current draw from the driver, and so that's where the constant voltage comes into play to provide that source with a constant and consistent power level from the driver, and it just kind of reduces that voltage to lower the output of those diodes. It is application specific typically, though, so it's really important to keep in mind that if you are picking a driver, to check with the manufacturer and ask, what's going to work better with this diode, because you can't just connect any diode to any driver and expect high quality performance. So making sure that you've aligned, whether it's CCR, CVR, or PWM, to the fixture and the diodes is going to be important to that selection. But in a lot of cases, manufacturers will provide recommended drivers before you even get to that point. Why compatibility matters is dimmability really doesn't mean dimmable. It doesn't mean universally compatible. It just means that it can dim to some degree, whether that's, goes from 100% to 90%, or it actually dims the whole range, really varies. So that term really doesn't mean a whole lot. So making sure that the controller, the driver, the luminaire, and all the wiring is in concert together is really the critical component there, verifying that compatibility to make sure that you have the best success for high quality dimming. And checking with the manufacturer, again, is always a good step, because they will oftentimes know or have a list of the recommended products to use. And if it's a new application or some kind of fundamental component to the success of the project, you might want to do a mock-up to kind of test out to see what that behavior is. Oftentimes I will mock things up with a new dimmer that I'm unfamiliar with, and sometimes it does show like, oh, this behavior is going to be really unsavory, and I do not recommend you use this dimmer. Whereas other times I might be surprised to find out, oh wow, that dimming is really good. I think that this is going to work really well for the project we're working on. So making sure that either you've confirmed with the manufacturer or done your own mock-up really makes sure that that compatibility is there, because that making, like, the compatibility really does become a critical function of dimming, and making sure that that is going to be a high quality dimming performance. So we talked about how things happen between the driver and the diodes, but now let's talk about between the driver and the controller, because there's a lot of different options there too. So the very first one that's recognizable is phase control, or phase dimming, which is where we are actually directly impacting the power running from the controller to the driver. And that driver is in an LED format, looking at where that phase cut is happening, where we're reducing the power, and interpreting that as how much power it should be providing to the diodes. Because of this, because we're affecting the power to the driver to communicate, low-end dimming on an LED tends to be quite erratic, because at that point we're choking the intelligence of its power source. And so that's why we typically have a lot of controlling for low end of the curve in phase control dimming, because of the fact that it is really unpredictable and can sometimes be really unattractive if we're not careful. So making sure that dimmable fixture that's phase controlled and the dimmer that it's being controlled by are compatible really makes sure that that lower part is optimal for the application, whereas the higher end tends to be not so concerning, although we do still see incompatibilities even at the full value, where the dimmer just for some reason creates a weird behavior in the fixture. 0 to 10 volt, on the other hand, is where we're now adding a separate circuit that is low voltage, sending a signal from the controller to the driver, giving it between 0 and 10 volts as the range for how intense the fixture is going to be. Digital protocols, we're now sending on a separate circuit typically a communication that is not just between 0 and 10 volts, but packeted data that then says, this is the behavior I want you to do, whether it's just, intensity values, or it's, go to this look over this amount of time. Depends on the protocol, but each digital protocol has its benefits and its drawbacks. Wireless systems, now we're talking about systems that use wireless communication. In a lot of cases, it's not that the wireless communication is direct to the driver, but rather to a module that then converts to typically 0 to 10 volt in North America anyways. And so it's not really a dimming method. It's a network communication protocol that then translates to a dimming method. And also something to keep in mind here is that in our industry, we like to use the term protocol to cover all of these different terms, but really it's only when we get to the digital level that we're really communicating using a protocol, which is a structured definition for how communication is going to work on a system. Whereas when we're talking about 0 to 10 volt and phase control, it's an analog communication method. It's not a protocol, but we just like to lump everything together. But whether what we select for our choice within the system really does affect its performance and flexibility. So phase control, we're stuck to circuits because we are controlling the power circuit to the fixture, and we're potentially limiting our low end of the dimming curve. 0 to 10 volt, we're still typically stuck to circuit, but our range of dimming can actually be quite more robust because we're not choking the power to the driver. Digital protocols were even more advanced and have even wider ranges typically of where we can dim to, and we might have elevated capabilities. And then wireless systems alongside digital systems as well have that robust communication capability. So let's just talk a little bit about application for these protocols. So phase dimming is most common in residential applications. And so you'll see, it's referred to as two-wire dimming sometimes, where you just have a neutral and hot. But in residential dimming, it just seems to be a very popular choice. And it's usually because we have screw-based LED lamps. It's also referred to as forward phase or reverse phase, or a number of other terms for what this is talking about, but typically with LEDs we see reverse phase, if you're drilling into it, being the better choice for phase control of LEDs. And again, making sure that compatibility there is critical to the success of the project. 0 to 10 volt dimming is much more common in commercial, especially in North America. Outside of North America, it's not so popular, but it is very common where we're seeing large groupings of commercial dimming fixtures. And it, again, uses that low voltage analog signal alongside. And it's widely supported by LED drivers. So instead of that term dimmable, we're actually seeing a little bit more standardization, again, with that dimming range, 100% to 10%, 100% to 1%. That's typically a thing that a lot of groups will actually put on their cut sheets and make sure that they're communicating clearly. And in most cases with 0 to 10 volt, we do require a relay to turn the fixture off because of that limitation of going only to 10% before you need to shut it off. Digital dimming, so Dolly is one. It's a addressable control. It creates flexible zoning opportunities, and it has monitoring capability so that you can see, how the drivers are reporting on the network. DMX512, on the other hand, is a very fast response type protocol. It has the ability to do really good, robust color control, and it can create scene-based applications. Dolly can also do scene-based applications, but in this case, we're talking more about like effects. So you hit a button and then it goes to, a color chase or something like that. Wireless dimming, so as I mentioned before, it really is more of a coordination and communication protocol than it is a dimming protocol. So you'll oftentimes see with a driver that has a module attached to it that's using wireless communication for the network, but then it's translating over to a wired protocol to connect to the driver. It's really good for retrofit applications. Because of that fact that you don't have to run wires everywhere, but you still have the dimming capabilities of whatever wire protocol you're adding. But it does require planning and commissioning because of the fact that wireless communication is reliant upon the space parameters. So if you're in a giant concrete warehouse and there's a lot of walls separating each space, you're probably not going to get really good coverage with wireless communication. Whereas if it were just, a standard open office with some plaster between rooms, that would be a lot more easy for a wireless signal to transmit throughout the space. So selecting a dimming method is not as difficult as it might seem. The very first thing we want to focus on is the quality of the dimming. Is it high quality dimming that we need? Do we just need to dim to a certain state to meet energy code? What is the goal here? So identifying that alone might be sufficient to get a sense of which dimming method we want to use. But then cost might come into play. There's a lot of debate right now in North America about which is more expensive, 0 to 10 volt versus Dolly. And we're seeing that there's actually some confusion, some, misidentification of pricing that might create some friction there. But additionally, there's just a lot of assumptions regarding Dolly. So it's kind of hard to pin down exactly which is cheaper right now, but you would be surprised at how inexpensive some systems might be using Dolly versus 0 to 10 volt. Compatibility. So again, if you want to make absolutely certain that the fixtures are going to be compatible, you might want to look at a digital protocol as opposed to a dimming method. Zoning requirements, do we need really fine zones, or can we get away with broader zones? Do we need to expand upon the system over time? Is there going to be a need to reprogram how the space is being used? Are there additional integration needs that we need to provide? So are other systems going to need to control the fixtures, or do the fixtures need to report to other systems information like how long they've been on for? And then maintenance requirements. Do we want our fixtures to be able to say, hey, I'm not turning on, or something's wrong, please, check the fixture out? We can do that with protocols like DALI, but we can't do that with phase dim or 0 to 10 volt most of the time. All right, so dimming applications and control strategies. Now we're getting into sort of how we're applying dimming. So the very first thing, code requirements affecting dimming. So daylight responsive control, multi-level control, partial on strategies, partial off strategies, demand response, functional testing requirements. We're going to go over all of these. So daylight responsive dimming. This is where we're reducing the electric lighting when there's available daylight, and it supports that energy code compliance for daylight responsive dimming. We want, if daylight's coming in through the window, we don't want artificial light on just because it's been left on. We want that light. If there's enough natural daylight coming through the window, we don't need those fixtures on at full output, so we adjust the intensity. So what it requires is identifying the daylight zones, identifying where the photosensors are going to be, which ones we're going to use, and what kind of programming we need to make that happen. So all of these factors go into making sure that daylight responsive dimming is possible. Multi-level control, on the other hand, is where we're creating multiple light levels with the control system. It's not just on-off. We're now adding additional steps, so it might be on 50% off. And it really is for the purpose of creating a comfortable environment, but also increasing our energy savings. You don't always need the fixtures on at full output. You can sometimes get away with 50% or at least a lower intensity than full output. And it can be step dimming. So again, could be just going from full to 50 to 0, or it could be a continuous dimming experience where you have a raise lower button and are able to kind of dictate like, oh, it's a little too bright, I'm going to dim it down, or it's not bright enough, so I'm going to raise it up. That's multi-level control per code. Partial on, partial off strategies are basically partial on means that the occupant activates a reduced light level, as opposed to walking into the space and the lights turning on to full output. They might just go to 50%. And so as a result, you're going to save energy by having partial on rather than full on, full automatic on. And then partial off is where the lights are going to go to a reduced level before or instead of shutting off. So you might have, for instance, a stairway that never turns the lighting completely off for safety purposes, but it might reduce how much light is in that space when there's no movement detected. And that way you still have safety covered, but you also are saving energy at the same time. Demand response is when we are now responding to a utility or a building signal, something outside of the system or part of the system that says, hey, there's an event that we want to reduce how much load we're using. So it's temporarily reducing that lighting load, how much energy we're using in that space to kind of compensate for something. And so in a utility triggered demand response, also referred to as automated demand response, we are creating an event that reduces the load in the building so that the grid is more stable. And this is more common in places where energy is a more challenging thing to manage, such as in California. And so with this utility triggered event, the utility can say, we're near blackout or brownout conditions, and we're just going to kind of trim a little bit of the load off to give the grid a little bit more breathing room so that we don't overload everything and lose all power because we've just blown past our limit. But it also helps meet the sustainability goals of the building. If the building is trying to make sure, like, oh, during peak lighting conditions, are we really needing all of this lighting, or during high load demand on the grid and where the costs are much higher for our building, can we reduce that demand from the building to the grid, or just in general to offset how much power we're drawing or how much we're getting charged to function. So it has a lot of dynamic capabilities. It's not as commonly used as it probably should be, because it's a very dynamic way of adjusting, but it's also a very noticeable way if it's not done correctly. So because you're dimming the lights due to an imperceptible reason, so you can't see how much power the building is using unless you rig up something special to show that off, odds are people are not going to understand why the fixtures are reducing their output, and so that could be a nuisance situation rather than it just being saving energy. People might go, oh, the lights are dimming on me, I need to go over and turn them on to full output. So you might actually have an opposite effect. So making sure that it's done appropriately and in a way that maintains that occupant comfort can be kind of challenging. So it's not an easy application in all cases. So speaking of manual control, though, manual dimming is when we're giving the occupants the ability to adjust light levels. This is the most traditional format of dimming that we've seen, where you just have something on the wall that you can interact with and you can adjust the light levels. It might be a wall box dimmer, it might be a keypad, it might be a touch screen, or you might have an app on your phone that gives you that ability to just manually adjust how bright the fixture is. But it really gives that user that ability to raise or lower the output, create more comfortable visual conditions. So again, too bright, too dark, they have that ability to adjust to that. Or they might just want to have different lighting conditions for different tasks, such as if you're in a conference room, you might want to have different intensity values for one area, such as the presentation wall versus on the table. And then again, we might have that energy use reduction when full output's not required. So people could manually adjust the intensity of the lights in their space if they don't need them on at full output. They can save energy by making that reduction themselves. So scene control is a little bit more advanced than just manual control, which is where we have preset light levels recorded into a scene. Typically, it's a one-button operation where you just push a button and then it goes to that pre-recorded look. And it is meant to be for recurring activities. So, again, in a conference room, if you want one zone that is dimmer because it's the presentation area and then the rest of the space, but then later on you want that zone to be full output, you can have multiple buttons that give you that ability to just return to that look that you had before. Automatic dimming applications, on the other hand, we're now talking about things that don't require human intervention: daylight harvesting, lumen maintenance, adaptive compensation, demand response again, scheduled dimming. So lumen maintenance is where we are now trying to compensate for something that is harder to measure, but something that's important to keep in mind, which is the fact that over time, the amount of lumens a fixture provides will depreciate. And so when we make sure that we have enough, maybe even a little bit more than we need lumens in the fixture, we can trim with high-end trim that top range out. But then over time, we can bring that value up so that high-end trim will increase from, say, 80% to 100% over a determined amount of time, because those diodes are going to depreciate how much they're providing, and this provides more consistent illumination over the lifespan of that fixture. Adaptive compensation, on the other hand, we're now making sure that the lighting adjusts based on the conditions of the space and the applications of the space. So it might change with the time of day. So depending on, you might have, again, in the morning, not as bright, midday, you might have either brighter or dimmer depending on the daylight conditions, and then at the end of the day it will adapt as well. So time of day can be a reason to have adaptive compensation. Occupancy patterns, depending on, in an open office you might have, somebody who's working in one end of the open office and then another person enters on the other end. You might have the space in between just brought up to a little bit of a level, but the spaces they're actually using will have the full intensity required for their function. And so you're adapting to the occupancy patterns of that space. Or you might have operational needs that you need to adapt to, whether it's based on the task, whether you're in a workshop and then suddenly you need a lot more light in one specific area. But the thing here is that it's not daylight harvesting. It's not where we're doing the daylight responsive dimming. We're now doing something that is more specific to some other behavior outside of how much illumination is coming into the space. So color tuning. So this is when we start getting into not just the intensity of a static white fixture, but we're actually going to either tunable white, dim to warm, or color changing, where we're impacting that hue of the light coming out of the fixture, not just the intensity. So tunable white is when we're adjusting the correlated color temperature, or CCT, of that output to match the black body curve, which is typically white light. You either have warm or cool or somewhere in between. And this is typically an occupant comfort thing. A lot of people have strong feelings over cooler or warmer color temperatures, and we've seen some evidence to indicate that having that ability to adapt the color temperature throughout the day might impact people's health and well-being. So we see it common in offices, healthcare facilities, or education, where the effects of this light will be perceived over time. If somebody's in an office all day long, they will have the impacts of that color change or that tunable white over time. They'll see it. Healthcare, same thing. We've seen some benefits of having tunable white in spaces, especially for after hours, to keep the light more amber and prevent stimulating people's circadian rhythm. And so we are seeing sort of this new information about tunable white, but in general it still is more of a preferential thing than just like a health button. So it's important to just keep in mind, and research is coming out every single day, so keeping in line with what the research is actually saying instead of some marketing declaration, it's important to just think about why tunable white is applicable to the project that you're using it. Hospitality also uses it because they like to have this warming, cooling effect depending on the time of day specifically, because in the middle of the day you might want a cooler color temperature, give the space more airy, free feeling, whereas at night you might want to create a more intimate, more amber effect in the space. Dim to warm and color changing are different from this. Dim to warm is where we are basically locked into a dimming curve for both intensity and color. And so as the fixture goes down in intensity, it'll actually warm up the hue of the light coming out of the fixture. But that's usually locked in place. It's not something that you can modify. Whereas color changing, we're now talking about not just the white color of a fixture, we're talking about saturated colors and effects. Solid red, solid blue, or mixture greens and stuff. All of that is possible with color changing lighting, and we're seeing it in hospitality, entertainment, or facades, where we have this sort of aesthetic that we're trying to go for. It's not a good source for task illumination, but it is a really great way of creating variety within the space using light. All right, so design and documentation. So making sure that we're designing successful dimming systems isn't as isn't that tricky, but it's still something that needs thought and care. So the first thing again, define why are we providing dimming for this space? Is it energy code? Is it because the owner wants it? What is the purpose for this? And then establish that dimming range. How low do we need to dim to? What are the conditions under which we would be at that low end? Do we need a high end trim to either meet energy code or just energy sustainability goals? What is going to be the user interaction? Is it going to be a manual or automatic procedure for that dimming? And so making sure that we coordinate all of these controls early on really ensures that we're going to have a successful dimming system at the end. Coordinating the system after that, we want to make sure that we've identified the luminaires and what dimming they're going to have, what drivers they're going to be using, what kinds of controllers we're going to be implementing in the system, the wiring between all of these devices. All of this is critical to making sure that the system is coordinated correctly. Then we want to make sure that we have our sensors that are controlling, at least communicating to the system. They don't have to directly control the fixtures anymore. They typically will just communicate to the system, and then the system will control the fixtures. What kinds of user interfaces, where they're going to be, what they're going to look like, keypads, what scenes are going to be programmed, is there going to be custom engraving? All of that still needs to be coordinated, just like any lighting control system. And so once we have all of this, we should make sure that the system is going to function together cohesively. But if we do all of this work, we should have a good functional lighting control system. Dimming zones, we want to make sure that we've identified how luminaires are going to be grouped together and whether they're going to be locked into that grouping or if we want a flexible grouping dynamic, such as through DALI. So when we're looking at the visual tasks and daylight conditions, how much window space is there in the building? How big are those windows? How deep do you think that daylight is going to penetrate into that space determines how big and how many daylight zones you want to have for that gradient to be covered. So if you want to learn more about daylight control, we already have a video, and I highly recommend you check it out, which talks more about zoning for daylight conditions, but also just thinking through the visual tasks. So in an open office, typically you're going to have visual tasks focused on the desks, but you might have a different space that has multiple variables of task conditions, such as in a workshop where you have a workbench, you have a saw, you have, a circulation area that might be flexible where you set up a temporary piece of hardware to work on. So thinking through, what kinds of visual tasks need to be addressed in these different spaces. And trying to avoid mixing incompatible loads. And what I mean by that is not, don't mix DMX 512 with DALI, which is hopefully an obvious thing that you shouldn't be doing, but also just in the sense of, if you have one 0 to 10 volt fixture from one manufacturer and another 0 to 10 volt fixture from another manufacturer, typically those are not going to work well when they're zoned together. You typically want to separate those out because odds are their dimming curves are going to be slightly different. Their intensity values are definitely going to be different. So mixing those together, you're just going to lock those into the same dimming, and that might not be what you want because of those variables. But when you're thinking through, also just think through what the occupant might expect. In a private office, they might expect all fixtures to be controlled together. But in a, conference room, you might have a pendant that should be controlled separately from the rest of the recessed lighting in the space. So there's a lot of things to think through when it comes to what the occupant might expect for their dimming zones. So scene design best practices. So now we're talking about making the setting, the look for the space, the pre-recorded effect. So we want to make the scenes make sense for the actual room use. If it's an open office, we might have, time of day kinds of settings, whereas in a conference room we might have, task specific settings, present, meeting, stuff like that. Classroom or a multi-purpose space, we might have to be a little bit more dynamic than that, where we're just saying, open, present, tight, some kinds of terms that really make sense to the occupants in the space, rather than trying to just do a broad brush control strategy and basically say, okay, well, they'll figure it out on their own, and so having conversations with the owners or the occupants of the spaces really does ensure that you're creating an ideal kind of outline of what is expected, but also what they might want. Sometimes teachers, for example, might have a custom need for a lighting look that would be really helpful for them to have a button that they could then associate to. And then making sure to document those levels and fade times, making sure that it's clear, okay, in the corridor, lights are going to fade over 5 seconds because we don't really need to have a very slow gradual fade. But in the auditorium, we might want a much more gradual fade to that blackout before the show starts. And then we want to double check all of this during the startup process, making sure that the programming aligns with what the owner expected, everybody's happy, intensity values are good and acceptable. So how we avoid dimming problems, because they really do kind of flare up randomly, it depends on the protocol we're working with. But the first thing, again, verify compatibility early. If it's phase dim, that might take some research. If it's a standardized dimming like Dali, that might not take as much research to make sure that the controller and the driver are compatible. But then make sure that the design documents are coordinated. The electrical engineer might state one thing versus the lighting designer versus the architect. So making sure that everything is cohesive can really ensure that there aren't any conflicts that arise or scope gaps that might appear. Make sure that wiring requirements are met. In some cases, the wiring requirements are very basic. You just need, 16 gauge wire. But in other cases, you might need specific cables and Belden numbers or something like that to really make sure that you're providing the right wiring. And make sure to coordinate with the manufacturer. Always double check with the manufacturer that the combinations you're working with are approved by them, or at least considered, and they say yes, that should work. If they say should, then I highly recommend you do a mock-up. But odds are the manufacturer is going to say yes, we've tested that before and this works, or we've tested that before and it doesn't work, or no, we haven't tested that and we can't tell you one way or the other. So doing those mock-ups really does support that goal of avoiding those dimming problems. So going specifically into each protocol, 0 to 10 volt has specific needs for dimming capability. We want to make sure, first of all, that the polarity is there. Pink and purple wires should always be connected to pink and purple terminals or screws or anything like that. Those are the two standard colors of 0 to 10 volt. And they indicate which pole they're referring to, so positive or negative. And so we just don't want to cross the positives and the negatives, because otherwise we're just not going to get dimming as a result of that. So that is a very common place where we find that 0 to 10 volt problems arise. We also want to maintain the proper wiring separation, so we don't necessarily want our 0 to 10 volt wires in with the giant conduit box with our line voltage power. Sometimes we can, depending on code, but we just want to make sure that we have that proper separation between the wires. We also want to confirm whether or not we need a relay to be able to turn the fixture off. We want to be able to validate that that driver is compatible, in the sense that there are multiple versions of 0 to 10 volt out there, and they're not all compatible. But typically in a commercial environment, so long as they're adhering to code requirements and manufacturing standards, the 0 to 10 volt should be compatible with the lighting control system by we've kind of figured out the issue with that compatibility, but it still doesn't hurt to just double check if it's a new application, new system, new fixture. Avoiding phase control problems is a little bit trickier and more nuanced. So matching the dimmer type to the load, forward phase, reverse phase, at least that is a good first step. But then we need to make sure that we're adhering to minimum load requirements, because if you only have 1 2-watt light bulb being controlled by the dimmer, that might not be enough load for that dimmer to function optimally, and you might get some weird behavior that way. So making sure that you're providing at least the minimum load on that dimmer. And then finally, just making sure that the low-end performance behaves the way you want it to behave. That, again, might be a mock-up situation, but it also could be a test report from the manufacturer just saying this is how low the fixture can dim to under these conditions. So just double checking that for phase control. Avoiding digital system problems, it's much more about addressing the zoning and programming for those systems to making sure that they are correctly done. It's less so much about the actual hardware as it is about the software running, but also just making sure that network communication is complete. So are they using the right cable? Are the cables terminated correctly? Do you have that secure connection between all the devices? There are some parameters that still need to be thought through with digital systems, but it's less about the hardware than it is about the software when it comes to digital. And then making sure that the installation personnel are properly trained. So in the other two, phase dim and 0 to 10 volt, we typically have just standard installation requirements, which might be one of the reasons why they're very popular in North America, whereas digital systems do require a little bit more training and knowledge to be able to implement correctly. Commissioning and functional testing, these are really essential to making sure that the system is running to expectations. And so we want to verify that dimming is smooth. We want to confirm that the trim levels are actually functioning, and it's not just reporting that it's at 90% of its total value, but it's actually performing at that level. We want to test the sensors and the schedules just like we would any other time. And we want to validate the scenes and the transitions between those scenes. So it's not enough to just say, yes, it goes to 50%, but does it go to 50% over 10 seconds? And then making sure that we're also adhering to the code requirements. So documentation that is required for good dimming really starts with the luminaire schedule. We want to make sure that we're identifying these luminaires have these dimming capabilities. The driver schedule. So if we have specific drivers that we're requesting, which drivers are we requesting and which luminaires are they associated with? Dimming zone schedules. So which zones are being controlled and how are they being controlled? Daylight zone diagrams. Where are the daylight zones and which fixtures are aligned with those daylight zones? Scene schedules. So what intensity values are the zones at per scene that we're recording? In some cases, it could be a guess, and then when we get to site, we kind of adjust that, but we want to make sure that we have something to start with. Compatibility documentation, especially again in phase controlled dimming, are we certain that there was testing done and that the fixture is compatible with the controller? And then there's the sequence of operations and control intent narrative, which I'm just going to do a quick overview here, but if you want to learn more about these documents, I highly recommend you check out our How to Design Lighting Controls 3-part series. So Control Intent Narrative, or CIN, that is the very first document that I recommend people who are new to lighting controls and dimming start with, because it's a plain language explanation of how the system is supposed to behave and perform. So it's just saying, I want my lights to dim to a certain, it doesn't even have to necessarily be to a certain value. It could just say, I want my lights to dim. And that way it's communicating, okay, in the private office, the lights should be able to dim. Sequence of operations drills a little bit more into that how and why. So, in the private office, it dims to 50% over 5 seconds. That's going to be documented in the sequence of operations. But the goal here is to define the expected behavior of the system. Between these two documents, we will have clearly outlined what is expected from the system. And it will also support the programming and testing, especially sequence of operations, because you'll have a document that you can point to as say, for instance, you're a service tech. You can then go, okay, this is what I need to do for this space. This is what I need to do for that space. And then as a commissioning provider, you can use that as a checklist for functional testing. But also, because we're providing these documents, we're reducing that construction confusion. We want to make sure, okay, in this space, this is the behavior we want to see. And so it clearly outlines to the manufacturer of the lighting control system and the contractor installing the lighting control system what is expected from that space. So there's a lot to go over, and we've just touched the surface of dimming. But in this part 1 of multi-part series, we really just talked about the capabilities of dimming. It provides a lot of flexibility, comfort, and energy savings, but we want to make sure that we're matching that application to the needs of the application. So which dimming is going to be most appropriate really is determined by the occupants using the space. So we want to coordinate and make sure that the dimming is there to enhance the user experience and the building's performance. And we do that by doing proper coordination, testing, and documentation. So thank you for joining me. Hopefully I'll see you in the next one. Before you go, a quick word about who we are. For over 25 years, the Lighting Controls Academy has served as the voice of the lighting controls industry. As a coalition of the National Electrical Manufacturers Association, or NEMA, we were created to help educate the public on lighting controls technology and real-world applications. Our hallmark program is our online education, including this video series, along with written courses through NEMA Academy. If you want to keep learning about lighting controls, head to lightingcontrolsacademy.org. You'll find articles, industry news, new products, award-winning projects featuring controls, and plenty of other helpful resources. Thanks so much for watching, and hopefully we'll see you in the next one.